Dear friends, welcome to session on Turbomachines on centrifugal pumps and compressors. This is module 5 prescribed by Vishweshwaraya Technological University, Belagavi. This is Dr. Rudresh from Mechanical Engineering, Government Engineering College, Krishnarajpete. In this session, I would like to concentrate on centrifugal compressors, velocity triangle or work done on air in a compressor, expression for a pressure ratio, losses and isentropic efficiencies in a centrifugal compressors. A centrifugal compressor is a machine which is used to supply a large quantity of air at a lower pressure ratio. It consists of a rotating impeller, diffuser and a casing. When you see the compressor, a compressor is basically a power absorbing machine. We need to drive the compressor with the help of a mechanical power, thereby to rise the respective a pressure head of a particular fluid which is handling through the respective system of a compressor. Therefore, a centrifugal compressor has to rise the respective pressure of a particular fluid that when we call that is the air into considerations, right? It consists of the different principal parts. What are those? It consists of rotating impeller, diffuser, and casing. Once again, there is a rotating impeller because it is a turbo machine, a diffuser, and a casing. You are seeing at this particular system. The impeller consisting of a disc on which the radial blades have been mounted. The impeller of a centrifugal compressor can be run at a speed of 20,000 to 30,000 rpm. Such a high speed is possible with the help of this particular compressor because it is a low denser liquid. These are all the machines which handles the low denser working fluids. That is the main reason why the compressor can run at a very high speed. So if you talk about this, so we have an impeller. Surrounding an impeller, we have got a diffuser. At the outlet, we have got a delivery section, right? At the same time, so in this case, when you see the compressor, there are two particular sections which you can expect in this case. One is the impeller section, the other one is a diffuser section. Finally, the casing will come into this scene. Now, when you see this, the diffuser, so we know that the rotating element of a particular compressor is an impeller, right, through which the respective the air has to interact. Okay, the diffuser is another important component of a centrifugal compressor, which surrounds the impeller and provides the diverging passage for the airflow, thus increasing the respective air pressure. The air coming out from the diffuser, which is collected in the casing, and then it is taken out from the outlet of the compressor. The air enters the eye of the compressor at low velocity and at atmospheric pressure. That is the inlet conditions of the air. It's very important concepts. The air moves radially outwards, passing through the impeller and is guided by the impeller vanes because the impeller vanes have been designed with respect to radial vanes. That means the respective vane angle at that particular system will be radial. It is exactly 90 degree. Okay. So what will happen in this particular system? When you see this impeller, the impeller increases the momentum of the air flowing through it and causing the rise in pressure and temperature of the air. Momentum of an air, that is very important, right? So that means we know that the rate of change of momentum is nothing but a force, right? Actually, we need a force. We need a work to be executed on the respective air so that the main what you can say the purpose, the main work of impeller is to increase the momentum of the air. So these are all some of the important parts which are participating in the game of compressing in case of a compressors. Okay, so let us think about the velocity triangle and the work done. For the best efficiency of the system, the air enters the compressor system radially at inlet. Therefore, guide vane angle at inlet is always 90 degree and no wind velocity at inlet of the compressor. Yes or no? When alpha 1 is equal to 90 degree, VW1 is equal to 0. Therefore, with usual notations for radial entry at inlet, alpha 1 is equal to 90 degree, VW2 is equal to VW1 is equal to 0. Sorry, it is not VW2, it is VW1 is equal to 0. Therefore, the inlet velocity triangle and the outlet velocity triangle with respect to this that we can write. With the same usual notations, we can write the inlet velocity triangle and the outlet velocity triangle. V1 is equal to Vf1. Therefore, the tangential force on the impeller per kg of air is equal to change of momentum of the air. That Fx is equal to Vw2 minus Vw1 by Gc. Vw1 is equal to 0 because the radial entry at outlet. Sorry, the radial entry at inlet. Therefore, Fx is equal to Vw2 by Gc. This is the force which is executed by the respective impeller. What is the work done by the impeller? Tangential force into the distance traveled. That is equal to Fx into u. That is equal to Vw2 into Vw2 into u divided by Gc. That means Gc is nothing but a force to work conversion factor whose value is always 1. Therefore, the work done per kg of air per second is equal to U2 VW2 by Gc, so much of Newton meter per second. Suppose, if the blades are radial at outlet, then the vane angle at outlet is 90 degree and the whirl velocity is equal to the blade velocity at outlet. This concept is very, very important. If the guide blade, if the entry is radial, if the entry of the fluid is radial, then the guide blade angles are 90 degrees. If the blades are radial, then the vane angles are 90 degrees. This is very, very important. So this concept has to know. When the discharge is radial at a particular section, the guide blade angle at that particular section will be 90 degree. Then there is no corresponding whirl. For example, at inlet alpha 1 is equal to 90 degree, VW1 is equal to 0. In case if the blades are radial or if the vanes are radial at inlet, beta 1 is equal to 90 degree and VW1 is equal to U1. The tangential velocity at that particular inlet is equal to the blade speed. So this is very, very important. VW1 is equal to U1. VW1 is not equal to 0 because the blades are radial, not the discharge. So this difference which we could have to make out while discussing about the turbo machines, irrespective of a type of turbo machines. When the blades are radial at, so in this case when the blades are radial at outlet means what? The blades are radial, beta 2 is equal to 90 degree. When beta 2s are 90 degrees, then U2 is equal to VW2. Okay. Therefore, the work done per kg of air is equal to VW2 U2 by Gc, so much of Newton meter per second. For an ideal condition, VW2 is equal to U2, that is U2 square by Gc. This is the maximum work which we can expect by the respective impeller. This is the maximum work done on air by the impeller. If the mass flow rate through the impeller is m kg per second, then the input power required to run the compressor is m into U2 square divided by 1000 into Gc, so much of kilowatts. Next is the pressure ratio. The pressure ratio is the ratio between the pressure at the outlet and at the inlet states of the compressor. The pressure ratio can be defined by considering both the stagnation state as well as the static states. Stagnation state means it's the total head pressure. The total head pressure, as a static state means that is at the initial conditions. Assuming the heat transfer during the flow of air through the impeller is 0 and considering the steady flow at inlet and outlet of the impeller. So in this case, what we can say is, I said that a compressor, a turbo machine system. In case of a compressor, the heat transfer during the flow of air through the impeller is 0 because more amount of the surface is not exposed to the respective temperature by that particular system. So we can assume that the heat transfer is almost negligible in that particular system. If that is the case, then we can say that the energy conversion through the respective turbo machine is under a steady flow process. Therefore, a steady flow at inlet and outlet of the impeller has to be considered for the analysis. Therefore, if we write the respective steady flow energy equation, we have the enthalpy H1 plus V1 square by 2 Gc Jc plus W, the work done is equal to H2 plus V2 square by 2 Gc Jc. Right? Therefore, when you solve for this W, H2 plus V2 square by 2 Gc Jc, this is nothing but it's a constant which is relating the heat factor with respect to the work factor. Gc, the work factor with respect to a force factor. The values of Gc is also 1, the value of Gc is also 1. Just it's a conversion factors. Minus of H1 plus V1 square by 2 Gc Jc. But H is equal to, I can write the enthalpy is equal to Cp into capital T. That means the specific heat at constant pressure times the temperature. Therefore, H1 is equal to Cp into T1, H2 is equal to Cp into T2. If you substitute this in the main equation, W Cp into T2 plus V2 square by 2 Gc Jc minus of Cp into T1 plus V1 square by 2 Gc Jc. But T01 is equal to T1 plus V1 square by 2 Gc Jc. This is the stagnation temperature at the inlet. This is the total head temperature at the inlet. Similarly, T02. Therefore, W is equal to Cp into T02 minus Cp into T01. In most of the situation, V1 is equal to V2. Right? So that is the static conditions. Then W is equal to Cp into T2 minus Cp into T1. If you solve for this, that is given by Cp. Take out T1 as the common factor in this case. T2 by T1 minus 1. So I can write the expression from thermodynamics. Relation T2 by T1 is equal to Pt by P1 to the power of gamma minus 1 by gamma, where gamma is equal to ratio of the specific heat of a pressure at the specific heat of a gases at constant pressure to the specific heat of a gas at constant value, Cp by Cv, the ratio of specific heats of gases. But the pressure ratio Rp is equal to P02 by P1, that can also be related to P2 by P1. Therefore, if you write that particular expression, W is equal to U2 square by Gc. You equate both W in terms of Cp, in terms of the work done for a maximum case. Therefore, U2 square by GC is equal to Cp T01, P02 by P01 whole to the power of gamma minus 1 by gamma minus 1. If you solve for P02 by P01, that will gives you U2 square by GC Cp T01 plus 1 whole to the power of gamma by gamma minus 1. This is the standard expression for a pressure ratio. Therefore, if you see the work input to the compressor, the work input to the compressor depends on the following factors. One is the mass flow rate through the respective system, the total temperature at the inlet of the compressor, the total pressure ratio of the compressor, which depends on the square and the impeller tip velocity. These are all some of the important the concept which we have to expect for a particular pressure ratio as well as with respect to a compressor system. The next is the losses and isentropic efficiency. There are many internal losses during the flow of air through the impeller. These losses may be the frictional losses between the air layers itself, right? There may be a relative velocity, right? Due to the relative velocity between the air layers, right? So there will be a particular type of friction which may be exist in a system, and the friction between the air passages, the friction between the air and the flow passages. That's also one of the important thing. Shock at the entry. All this effects causes the increase in enthalpy of the air without increase of pressure. Keep this in mind. So once when we are speaking about these particular losses, frictional losses across the blade passages, frictional losses across the fluid layers, frictional loss due to the shock at the entry. So all these particular situation will increases the enthalpy but not the respective pressure. Without increase of the pressure, there is a rise in enthalpy that has been occurred due to this particular type of we can call it as irregularities. Therefore, the actual temperature of the air coming out from the compressor is more than the temperature of the air if it is compressed isentropically. The actual work required for the same increase in the pressure ratio is more due to these irreversibilities. For this particular purpose, we know that lot of losses has been experienced by the respective system within the working zone itself. For that, we have to concentrate on what is the efficiency. So in this case, we are concentrating with respect to an isentropic efficiency as well as the stage efficiency. Therefore, the isentropic efficiency is defined as the ratio of isentric work to the actual work. It is the ratio of isentropic work to the respective actual work. So now we are looking at this particular graph. We have got the two states P1, the pressure P1, pressure P2. 1 to 2 dash is nothing but it's an isentropic state. 1 to 2 is nothing but it's an actual state. Therefore, see, when you compare the work done by the entropy, that means the isentropic process, it will be less when compared with the work done in an actual process for a respective centrifugal compressor. Therefore, the centrifugal compressors are one of the important compressors that we have to define. So, when you define this isentropic efficiency in terms of the work done, it is the ratio of isentropic work to the actual work, because isentropic work is always less when compared with an actual work. In terms of that particular work, I can relate the isentropic efficiency as the ratio of the respective isentropic work to the actual work done. So if we define this isentropic efficiency, so in this particular situation, H02 dash minus H01, this is nothing but the taking the stagnation enthalpy into consideration, taking the stagnation temperature into consideration, T02 dash minus T01 divided by T02 minus T01. If we consider the static conditions, that means V1 is equal to V2, definitely I can say that isentropic efficiency is always given by T2 dash minus T1 divided by T2 minus T1. This is the expression for isentropic efficiency. Okay, dear friends. So in this concept, we just concentrated on a compressor, different parts of the compressor. What is the work done by the impeller on the compressed air, on the respective air? At the same time, what is the meaning of a pressure ratio? What is the expression for a pressure ratio? What is the work input to the respective compressor? At the same time, what are the losses that has been experienced by the respective compressor? With respect to that, how we can define the isentropic efficiency with respect to a stage. So these are all some of the informations which we have discussed in this particular session. So in the next session, we will be bringing the more informations on this particular centrifugal compressors. Thank you.